So there was like a slide 240 to 243.
Okay.
In that one, can you explain how you got the polynomial time formula n cubed and why we are dividing it by epsilon?
Oh, I would say I haven't given you that at all. That's a complicated proof. Wasn't that for? That's for a knapsack problem, right?
Yeah.
240. That's a complicated proof that we haven't given.
Okay.
And the reason we're dividing by epsilon is because you can imagine so epsilon is the error,
Okay.
right? So if you have the smaller and smaller epsilon is, what we're promising is that your result will be within 1 plus epsilon, right? So if epsilon's 0.01, then your result will be within a factor of 1.01 of the optimal, right? So if epsilon decreases to 0, then it states you will get the optimal, right? So this is an algorithm whose running time is some reasonable polynomial in cubed, say, divided by epsilon. So if epsilon's 0.01, then 1 divided by epsilon is 100. So that's just 100 in squared, which isn't a big deal, right?
Okay.
But if you bring epsilon down to 0, then what happens to 1 over epsilon?
It becomes infinity.
It becomes infinity, right? So then that says that algorithm doesn't work, right? You have to go back to the 2 to the n algorithm.
Okay, and what was the point of the n cubed?
Well, I didn't. The point is that it's some reasonable polynomial. We didn't go into details as to why it was n cubed.
Okay. And can you also explain the exponential formula?
Yes. All right. So let's.
And slide 240 to 243.
All right. 240.
It's right there.
Yeah. So the running time is the number. It's always the number of sub-instances times the number of bird answers. All right. And here, how many sub-instances do we have is 1 for every entry in this matrix, right? Remember, this matrix has, for this problem here, we're considering the first I objects, only the first I objects, and we're considering a knapsack with volume only up to here, right? We're assuming the volumes in integers. So these are 1, 2, 3 integers up to V. So the number of sub-instances is n times capital V, right? The volume of the knapsack, right? Does that make sense? And the number of bird answers is 2, because for each object, she either says, yes, take it, or no, don't take it, right? So that's why this is the running time, right? N times V is the number of sub-instances, times 2 is the number of bird answers, right? Now this is why we're writing this down is because how many bits does it take to write down the input, right? Well, for each, ignoring, so you have, right? So you have n object. This is gonna be kind of the part of the size of the input is one of the things that you have to write down is the number of bits in your volume, right?
Mhm.
And not the number of bits. You have to write down your volume, and so the size of the description of your input is going to include the number of bits to write down the volume,
Mhm.
right? So you could say that this was the size of the input, and this with 2 to it is equal to v is the integer value, right? Remember, if I wrote down some integer here, right? I'm going to write down, here's some integer. How long does it take me to write this integer is proportional to the number of digits, right?
Mhm.
But if I asked you to count 1, 2, 3, 4 up to this number, right? The universe will have burnt out by the time you're done,
Mhm.
right? If I add an extra 0, an extra digit, it's only one extra work for me. It takes me one more bit to represent the volume, but your time goes up, right, by a factor of 10 or a factor of 2, right? Does that make sense?
Yeah,
So
that makes sense. Oh yeah, for like the knapsack problem, I was a bit confused because like very earlier on in this chapter, you said that the dynamic programming is like different from like the little bird algorithm, because in dynamic programming you would be trying like every single solution, whereas in little bird you would be basically asking the little bird, hey little bird, which next step should I take?
right.
So with the knapsack problem, it was actually using like little bird, like it was
Yeah.
asking little bird. So I was a bit confused, but because the site title was like dynamic programming, and then the Pooh Bear was basically asking the little bird and his friends to make next steps. So are we taking dynamic programming as the bird and friend algorithm?
Yeah. So what dynamic programming is, you can describe it in a number of different ways. But I think anybody would agree that there's in dynamic programming is you have one instance that you want to solve, and in order to solve it in a kind of recursive backtracking sort of way, you're going to have all these sub instances, right? And so if the total number of sub instances that you ever have to have turns out not to grow exponentially, but only to be polynomial, right? Then we can form a table where there's one cell in the table for each of your sub-instances. And so I think if you were to go to a random person who knows dynamic programming and say, what's dynamic programming? They'll say, well, there's a table of sub-instances and you solve them from smallest to largest, right? So that's one concept of dynamic programming. And when we're talking about the Pooh Bear story, then these sub-instances become states of a graph. So, all right, so actually let's stick on about dynamic programming. So another thing about dynamic programming is it's not just, I mean, Fibonacci, if I wanted to compute Fibonacci numbers, you know, Fibonacci is the sum of the previous two numbers, right? So there, I could call recursively. I want to know my instance is n. I get my friend to compute Fibonacci of n minus 1 and another friend to compute Fibonacci of n minus 2, and I add them together, right? So if we do that recursively, can you imagine it grows into this big exponential tree? Right? Because I have two friends, and they have two friends, and they have two friends, and it goes to a depth of n. Right? But it's much better to solve it by not so memorization comes from the word memo, is to take notes of solutions that you've solved before, right? So a better way to compute the Fibonacci numbers is to compute Fibonacci of 0 and 1, and then add those together to get the Fibonacci of 2, and then of 3 and 4 and 5 and 6, right? And that's kind of more the way dynamic programming, memorization, fills in the answers one entry at a time, right? Does that make sense?
Yeah, so basically we can use like Bird and Friend algorithm interchangeably with dynamic programming.
Well, now let me keep, I'm telling you all the various pieces. Now there's another piece to dynamic programming. I wouldn't call Fibonacci numbers, I wouldn't call that dynamic programming, really. You could, I suppose, but because there's another aspect to dynamic programming, which is that I have a number of things to try, right? I might try, I have to decide for each object whether to put it in the knapsack or not. So I'm going to try putting it in the knapsack and recurse, and then I'm going to backtrack, and I'm going to try not putting it in the knapsack and backtracking, right? So that's another aspect of dynamic programming, is that you're trying different things, right? And so those are two things about dynamic programming. One is a table of subinstances that needs to be solved, and two is there's this idea of you trying things. All right, so you could just be happy with that and write code for dynamic programming. That would be fine. That would be a standard way of doing it. Now I've told two different stories, and you can decide for yourself whether those stories help you or not. The story I focused on in the past, and we're talking about it here, is the idea of the bird and the friend. So the bird is the answer is you're going to try different things, and the question to the bird is, which of these things is the best to do? So you can ask the bird, should I take the one object, or should I not take it? And then her answers are yes and no. And since we don't actually have a bird, then you try them all. So is that a useful story to you or not? And then the idea of a friend is, once the bird tells you yes, take it, or no, don't take it, then you believe her, and because that's what you're trying now, it's the case you're trying, and that helps you reduce the problem to a subinstance. And that's where the friend comes in, is you ask your friend, how do you give me the rest of the path? How do you fill in the rest of the knapsack? So that's the idea of the bird and friend algorithm. So the classic, maybe the easiest to understand dynamic programming is finding the shortest path from S to T. And so in that case, every node of the graph is a subinstance, and the edges are the things that you're trying. So if you're at T, you can say, bird, which is the last edge that will give me the shortest path from S to T, right? I say, bird, you have a path from S to T that's shortest. What is the last edge in it? And if the bird tells you which one and you try it, then you step along that edge to some node V, and there's a subproblem. What's the shortest path from S to V. And so the subinstances correspond to nodes in your graph. So there's a correspondence between subinstances and nodes in this graph. And one way that I think many researchers, not just me, I've talked to friends and they agree about this, is one way of thinking about dynamic programming, even if you're not solving a graph theory problem, but you're trying to solve longest common subsequence, or you're solving the Natzer's problem, all these examples that we did. It's useful to think about reducing the problem to the graph, a path to the graph. So then whatever your problem is, the subinstances correspond to nodes, and the edges correspond to things that the bird might tell you which way to go. And then I added on top of it this extra story that if how am I going to understand this graph is you're walking from state to state. You call the nodes states that you might be in, and you walk from state to state in this graph. And then you can think about the name of the state is being, well, what do I have to remember as I'm traveling through life? What does Pooh Bear have to remember about what he's seen so far? How are you doing, Sunda? So did you follow any of that? I couldn't see you anymore.
Yeah, I'm following.
Picture. So it was harder to know if you were following.
Yeah, I'm following.
Did that help? Are you?
That helps. But I'm still a bit confused if like they are the same thing.
Well, I would say that they're really two things. The one thing is the subinstances are the same as nodes in the graph are the same as states that you might be traveling through. Those are all the same thing. Another thing that's the same is in dynamic programming, there tends to be the solution to this problem. Let's see here. Let's move your faces that are in the way. And short code. So this is kind of a recurrence relation, right? It says it's the optimal solution. We're gonna for every integer I, we're gonna have a problem to solve, right? And the solution for problem I is going to be, here we're taking the best of a bunch of things. We're going to try a bunch of things. For every k, say less than I, we're going to try a bunch of things. And so that's kind of like and when you're trying a particular thing, then you ask your friend for help. And here I get advice from the bird. I'm trying something, then I ask the friend something. And that is it's a recurrence relation. It's just like the ith Fibonacci number is the sum of this Fibonacci number and that Fibonacci number, right? It's a recurrence relation. And the solution for instant I is, once we know which k is best, is a combination of the answer we get from our friend and some information corresponding to which one is best, right? Which the k is, which one is best. So this here, you can think about as the definition of dynamic programming. And if if it helps you, then you can have each of these subinstances be a node or a state or a subinstance, and you have these different k for each subinstance I. We have various things to try, and these k's correspond to edges coming out of node I. Right, so you mapping it over to this here, right? We're looking for the best path from S to T, and so then for every node of the graph, there's a subproblem which says what's the best path from S to that node, and how do we compute it? Is here let's see if we can go back and back here. Let's see. So suppose we've already answered all of these ones. We know what the shortest path from S to each of these nodes is and what its cost is. So then we fill in the next one. And how do we fill it in? Well, there's going to be a bunch of things to try. And so if so she's going to, here's our bird trying to solve this answer and wanting to find the last edge. Well, how does he get this answer in this last edge? The way he gets it is he wants to know which is the last edge first. So he imagines he's asking the bird, but he doesn't have a bird, so he tries them all. The bird might say this edge, in which case, what's his answer is he asks his friend for the shortest path to V4, which is going to have length 8. He adds the 2 of this edge to get a possible answer of 10, right? And then he tries this bird answer, and he combines the 2 with the 7 to get a possible answer of 9. And then he tries this bird, this answer, and combines the 5 and the 6 to get 11, right? And so after he's done all 3 of them, he knows for each possible bird answer, what is the best path from S to his node consistent with that bird answer. And what he does is he takes the best of those, right? Does that make sense? That's dynamic programming.
That makes sense. So basically, when we would be like writing the code for the little bird algorithm, like on slide 72, you actually wrote like a code format for the dynamic programming. So for the little bird, like bird friend algorithm, that would be like different, or that would be similar format.
All right. Well, why don't you name one of the examples, and let's
say the knapsack bird friend
problem.
Algorithm.
All right, so let's do the knapsack problem. So where are we? Knapsack.
It's right above event scheduling.
Yeah, there it is. Thank you. All right, so here, let's go through this problem, and I will tell you, if this is the problem, what the test would look like. Okay. So I'm going to tell you what the instances are, right? In this case, the instances are a bunch of objects in the volume of the knapsack. I'm going to tell you, there's an example of an instance. I'm going to tell you what a solution is. In this case, the solution is a subset of the objects, right? So for each object, you have to decide whether to take it or not, right? So implicitly, a solution is a sequence of decisions, right? And so solution here is a subset of the objects. I'm going to tell you what the value, when a solution is valid, right? And in this case, the solution is valid. The solution, remember, is a subset of the objects. So here, if you do a sum over all objects in your solution of the volume of the object that you put in, it doesn't exceed the volume of the knapsack, right? So that's what I mean by the solution being valid. Then I'm going to tell you the cost of the solution. In this case, it's the sum of the costs of the objects that you put in, right? All right, so now I'm going to ask you to solve this problem. Actually, I'm going to ask you to solve it in 3 different ways, right? And you may hate me for this, but I think it's good to understand these ideas in 3 different ways. And I'm thinking about even adding a question that doesn't have any marks, which you can then say which way you like and how much grief this is causing you. But the 3 different ways are: 1, to kind of think about it as a game of life, and then 2, with nodes, states, nodes which are states, and edges, and then also to think about it as the bird friend algorithm, and also to think about it as how you would code it up, right? So those are 3 different ways of thinking about the same problem. All right, so first, here's that's showing it's hard. So if we are going through the game of life, then you might think, all right, suppose the reason I like this is it kind of relates more to how you might think about the problem, right? You personally, you are trying to solve this problem. How are you going to solve it? Well, you're going to walk through the objects one at a time, and for each one, you're going to, especially how you would solve it if you had help from some divine inspiration, right? Somebody who can give you just little hints along the way. As long as it's just a little bit of a hint, then how would you solve it? Well, you would go through the objects one at a time. And when you get to this object, you would say, do I take it? Do I not take it? And the little bird will tell you whether to take it or not. And if she says to take it, then what do? You put it in your knapsack, right? And then you move along to the next object and you say, do I take it or not? And she says, don't take it, right? So doesn't this feel like a pretty natural thing to do if you had help of a bird, right? It's a story. So that's great. So now we want to think about, okay, great, but how much, as Pooh goes along, he's going to go from state to state, right? A state tells us everything he knows, right? The name of the state. If you took 2001 from me, you'll know that I name the states by what I know. So what does he need to know? Does he need to know how many of the objects, which objects he's on now? Right, definitely. Does he have to remember which were kept and which were not kept? Well, no, that would be far too much information, right? Because that's n bits of information, so we need 2 to the n states, which we don't want an exponential number of states, right? So that's way too much. Now, we do need to know, so what he needs to know to proceed is he does need to know how much of his knapsack is filled so far, right? Because that does influence the future, right? So he's going to remember that. And so now what are our states? So one of the things I'm going to ask you in the first question is I'm going to say, think about this story of going through here, right? Maybe you have fingers on your input and you're moving your fingers around. Maybe you're thinking about the input in some sort of order and you're asking questions to the bird, right? And then the states, which are also going to be our nodes of our graph, which are also going to be our subinstances, is going to tell you what Pooh Bear knows so far, right? So right now, what does he know? Well, he knows he's considering the ith object, and he knows he's filled J of the knapsack so far, right? Does that make sense? going forward, you could say, instead, you could say, how much knapsack does he have left to fill, right, is V minus J. So you could think in terms of how much knapsack do I have left, how much knapsack have I filled so far. You can think about that either way. But anyway, here he's sitting, right? And now you say, this is the state I'm in. This is the node of my graph. This is the subinstance I need to solve, right? As a subinstance, you can think about it as forward. What do I still have to do? Or you can think about backwards. What you could think about this is, what's the optimal way of storing the first I objects when I have a knapsack of size V, of size U, right? That will be my subinstance coming backwards. All right, does that make sense?
So this part is like the game of life example, not the
Yes.
bird friend algorithm.
Well, there is still some bird happening here, right?
Yeah.
So the bird then comes in. He asks this object I, do I take it or do I not take it, right? If she says, no, don't take it, then where does Pooh Bear go? He follows an edge down to where? Well, he's now considered I plus one objects, right? So he moves down, but his knapsack hasn't changed volume, right?
Yeah.
Now I'm going to label that edge with how much does it change the value of my solution, right? Every path through the graph will be a solution, right?
Yeah.
Because here, if I follow this edge, I'm deciding in my solution not to take this object, right? So how much does that contribute to my solution? It contributes 0 because I didn't take it, right? So now the other option is I could ask her and she could say yes. Well, if she says yes, then you can imagine what Pooh Bear is going to do. He's going to put the object into the knapsack, right? And then that changes his state. Why? Changes the state down here. What's his new state? Well, he's now ready for the I plus first object, right?
Yeah.
And his knapsack has volume VI bigger than it was before, right? So this shifted over by integer 1, 2, 3 up to VI, and it went down by 1, right?
Yeah.
Now, what is the incremental cost to our solution? Well, our solution went up by the price of the object, right?
Yeah.
So if I was following this, right, I start here, where here I haven't considered any objects yet, or maybe I'm ready to consider the first object, and oh, here I guess I'm ready to consider the first object, and my knapsack has nothing in it so far, right? That's where I start. And then as I follow a path through this graph, right? Every time I take a step, I will be deciding which way I go will decide whether to take the object or not, right? Does that make sense?
Yeah.
So can you see that every path through this graph corresponds to a solution as to what to take and what not to take, right? And the cost of that path will correspond to the cost of the solution, right? Does that make sense?
Yeah. So basically, the difference between like a bird friend algorithm and then the game of life is that in bird friend algorithm, you would have both the friend and the bird to help you out. And in
Let's
the game of life,
understand this one first,
okay.
and then we'll do it again. All right? Do you understand this game?
Yeah.
So what I'm going to ask you is tell me a little bit about your story of Game of Life. And you'll say, well, I consider each node one at a time, and I ask the bird whether to put it in or not. And then I'll say, what am I remembering? What does Pooh Bear remember? And you'll say, I remember how many objects I've considered and how much volume I filled in, right?
Mhm.
And then I'll say, what are your states? And you'll say, well, for every I and every J, I have a state.
Mhm.
Then I'll say, what are your actions? Well, I either don't put it in or I do put it in. I'll say, what are your edges? Where do they go? Well, I describe this graph, right? I go from node ij, I either go to, I have two edges, one that goes to I plus 1, j, right, with weight 0, or I go over to this node, right, I plus 1, j plus vi, right? And it has weight this. That's how I'm gonna describe I'm gonna ask you about this graph. I'm gonna ask you, what is node 0? What is node S? And you'll say, well, I'm considering the first object and I put nothing in my knapsack, right? I'm gonna ask you about node T, and here you might say it's a little trickier. And in fact, I'm gonna give you a little warning. And the little warning is going to say, give some extra thought about edges into T, right? And why do I do that? Is because often there is a problem there. And you see, in this case, the problem is, suppose the Pooh Bear ends up in this state, right? Then that says, well, he's considered all the objects, but his knapsack is not completely full, right? And that's okay. We're not requiring him to absolutely fill the knapsack if it wasn't useful to him, right? And so we put in these extra edges of weight 0 to say, if your knapsack's not quite full, even though you've considered all the objects, then just fly over and pretend that your knapsack's full, right? And that gives me one state here, which says, I'm done. Node T, I'm done, right? Does that make sense?
Yeah.
That gives me a graph. And so then one way of thinking about the computational problem is...
Sorry, Professor, I'm still need to confuse for that.
All right.
For every subinstance, how should we trust the bird, or why the bird decided for every step, the subinstance?
Right, it's exactly. So in this, you never can trust the bird, right? We don't have a bird. When we talk about the story, we like to pretend we had a bird that would help us, but we don't have a bird, right? So in this case, if we had a bird, she would tell you how to walk through this graph, right? But what is our goal here? Our goal is not to find the shortest path. It's not our goal, because we don't know how to do that. We don't have a bird. Our goal is to make the graph. Our goal is only to define the graph. And what we need to be true about this graph is that there's a one-to-one mapping between paths from S to T and solutions to our problem, right?
Yeah.
You see, for every path, there's a solution of what to put in the knapsack, right? And for anything you put in the knapsack, there's a path in this graph, right? Does that make sense?
Oh yeah, I got it. Thank you.
Right? And they have the same cost, right? The cost of the path is the same as the cost of the solution, right? Does that make sense?
Yeah.
All right, so now we form this graph. Now we still don't know how to solve the problem, right? But we've expressed our problem, right? We were given this graph theory problem that we didn't know how to solve. And instead of solving it, we express the problem as a different problem. Now we have a brand new problem, which is, how do I find the shortest path, the longest path from S to T, right? Because the longest path will put as much in my knapsack as possible, right?
Yeah.
Right, so you see, I haven't solved the problem. Don't think I've solved it, but I've changed the form of it. I've changed it into a form that we can understand in a different light, right? Does that make sense?
Oh yeah, thank you.
Right, so now suppose that you are a person in industry that needs to know what to put in your knapsack, right? But you have for you an oracle that can solve the shortest path problem. So what you do is you say, I need to solve the knapsack problem. So the world is going to give me an input to the knapsack problem. The world tells me the volume of the knapsack and what my in objects are. And my task is simply to form this graph. I have nodes and edges in my graph, right? And then what do I do with this graph is I give it to the oracle. And what does the oracle give me? She gives me the longest path from S to T, right? Now, we don't care how she does it. Right now, that's not our problem, right? What do we do with that path? Well, that tells us which objects to put in our knapsack, right? And we know that since there's a one-to-one mapping between solutions to this problem and solutions to this problem, and their costs are the same, if she gives us the optimal path, that will give us the optimal way to filling the knapsack, right? Does that make sense?
Yeah.
All right. So.
Hi. Hi, Jeff.
Yeah.
Is it like the build part is essentially like careful brute force? Is it like just brute forcing the problem?
Which is?
The build part.
Finding the path?
No, like building the paths. No, I mean like constructing the graph.
Well, the graph is really straightforward, right?
Yeah.
If you ignore the fact that the volume might be big, right? The graph is just how many nodes? We have n times v nodes. And you can, for each node, you can say what the edges are, right?
Yeah, and it's like there's two ways of thinking about this. So one is like one is a bottom up fashion. It's like so we've already like filled up a knapsack that of size this large, and we're moving forward to like so we're adding more space to it, and we're trying to solve a bigger problem. Or the other way to think about it is to like think of it in a top down fashion, like.
Well, here I'm thinking about this entire graph, and then I'm going to have some oracle find the path for me, right? So I think it's more, this is a holistic way of thinking about it. Well, I guess it's, I think about it moving forward. Kuber moves forward and makes decisions, but he doesn't know how to make those decisions. But we're just listing the decisions he could make and the actions he could take and what states he would be in as he makes those actions. And that gives us the graph, right? And then the graph, ideally the graph's not very big. So writing down the graph is not a problem, right? If it's not a big graph, if it has a reasonable number of nodes and a reasonable number of edges, the running time of our algorithm will be the number of edges, right? Because we're writing down all of these edges.
Yeah.
Right?
Yeah.
So we write them all down, and then the oracle is going to find the path for us. Right? Does that make sense?
So it's like as he walks through like the path, he's essentially exploring all like possibilities, like in a brute force fashion.
No, yeah. So you keep going back to wanting Pooh to have a method. He doesn't have a method.
Yeah, but yeah, that's what I meant.
How he decides which way to go.
Yeah,
right? That's not his job. So you can imagine the bird tells him which way to go. All we want to know is track out where he might end up in his decision making.
Yeah, so he doesn't know which way to go, so he chooses to like brute force all options.
No, don't stop saying that. Stop saying brute force. We will never do brute force. If you say you're doing brute force, I will give you a 0.
Okay, fair enough.
Never, we do not do brute force. That's
Like-
exponential.
Like not real brute force, but like
Don't say fake
like
brute
he's-
force. We don't do it. His job is not to find out. In this case, we're just laying out the graph, right?
yeah,
We're saying if he ends up here, right? I don't know whether he will end up here or not, but if he ends up in this state, what state is it? It's the state that he's ready to consider object I in the knapsack's full, right? We're saying if he happens to be in this state, what decisions, what actions might he take? Well, he has to decide whether to take the ith object or not. So one possibility is no, and one
Mhm.
possibility is yes. And in those possibilities, where does he end up? Right? I'm just laying out the possibilities. We're not making any decisions yet. We're not saying how those decisions are made. We're just listing. It's like, think about it this way. The first thing you should do in the morning is to make a to-do list, right?
right.
And all you're doing there is writing down the things that you plan on doing the day, right? And
Yeah,
sometimes there might be some ifs in there, right? You say, well, I don't know whether my mother will call me or not, but if she calls me, then I'll do this, this, and this, right?
yeah,
If it rains, I'll put on a raincoat, right? If it snows, I will get my winter coat back out, right?
yeah.
Right. So have you made any decisions yet? Have you done anything yet?
No,
No,
no.
you're just making a to-do list,
Yeah,
right? So all I'm asking you to do here is to describe your to-do list as a graph,
yeah. Okay.
right? So
Yeah.
what does the graph look like? It lists all the places you might be in today, right? It says here, if my mother calls me, and if I ever have to consider the ith object while my knapsack is filled by Mount J, then what I'll have to do is I'll have to consider either not putting the object in or putting the object in. I'm just listing the possibilities, right?
Yeah,
Here's another version. I'm really bad at making decisions. And if a friend phones me and says, hey, we're going to go for dinner tonight, where do you want to go? I will freeze up in knowing where to go, but I'm really good at making lists. So I'll say, well, we could go to the Indian one, or we could go down to Koreatown, or we could go to the Japanese place, right?
yeah.
Now, I haven't
yeah,
made any decisions. I've just made a list,
right.
right? And so
So-
that's what we're doing here is we're making the list.
Yeah.
Right?
So it sounds more correct if I say I'll list out all the options instead of saying like brute forcing
Yes,
all the.
yes.
Yeah, I guess that's what I meant by brute force. Like
Right. All
list
right.
out.
Well, now the brute force is that there are an exponential number of paths,
Yeah,
right? And I can't consider all the paths.
yeah. So what I meant was brute forcing all the options, like not the sequence, like not the actions.
All right. Well, let's just stop talking about brute force. Let's
Okay.
just say there are a lot of paths. There's an exponential number of paths. And there are
Right.
a lot of solutions about
Yeah.
what to put in your knapsack. But there's a one-to-one mapping between them. Right?
Yeah, yeah,
In some way, you're right about brute force in that in some ways, I've encoded in this graph all possible solutions, right?
Yeah,
you might say it would be not first step in solving this problem is to list every possible solution, right? But they're an exponential number, then we can't write them down. So we're going
right.
to write them down in a coded way. And the coded way is by writing a graph so that every path corresponds to a solution.
Yeah.
Right?
Yeah.
All right. So once we have this graph, which somehow encodes all our solutions, then we come over here and we get our oracle to find us our shortest path for us.
Yeah.
Does that make
Got it.
sense?
Yeah, it does. Yeah.
All right. Any questions about this graph, or should we go on to here? The running time is the number of edges in the graph, right? So it's the number of states times the degree of the node. All right, so let's go on to coming up writing code. All right. So the way I given the code, you know, in real life, you wouldn't necessarily have to write code. You could write code that solves the shortest path problem and then just put your graph in there. But maybe what you want to do is write code which is going to solve it directly. All right. So let's go through and see what the code is. All right. Can people read? Can you read this? Is that font big enough?
Yeah, it's readable.
Yeah.
All right. So the code has the following pieces. The first piece is what is the input, and I'm not going to make you give all this code here. I'm going to only ask you for key parts. So when we get to the key parts, I'll tell you what the key parts are. But someday, maybe on the exam, I'll make you write the whole code. So it's good to know. So here, what is my input, right? My input is the volume of the whole knapsack plus these objects, right? And what are we trying to find? We're trying to find the optimal way to fill the knapsack with the total greatest possible price, right? So then I always write this paragraph here. I first, and this is all commented, right? That's the percentage means this is all just chatting to the world, right? And the first one says, first thing is, what are all my sub-instances and how are they indexed? All right, so here I'm indexing my sub-instances by a V prime and by an I. So V prime, before I use J, here I'm using V prime. It's the same idea, right? And what is this sub-instance? It says, what is the optimal way to fill a knapsack whose volume is V prime? So you don't have the full knapsack, you only have V prime of the knapsack. And you don't have to fill it with all the objects, you only have to put in, you only have to consider the first I objects. All right, so that's a sub-instance. Everybody get that part?
Yeah.
All right, remember, those are the nodes of your graph. Those are the states that Pooh Bear was in, is all of these things. And when I talk about turning things around, you know, forward, backwards, that gets all very confusing. What I mean by it is when we write down the sub-instances, we want to write it down in a way that's as user-friendly as possible, right? So it's user-friendly because I'm talking about the first I objects, not the last I object, right? I'm talking about, oh, my knapsack only has volume V prime. I'm not saying it's a bigger knapsack and I filled up so much of it already, right? I'm making it into a nice user-friendly, aesthetically pleasing sub-instance, right? You know what I mean by that? That's the whole turning it around thing. Is everybody comfortable with that? Yeah, Sundance, you good?
Yeah.
All right. Then we're going to say, hey, what we would like to do is have a table where for each subinstance, we store the optimal solution, right? But the solution's too big, so we're not going to store it. We're only going to store what is the cost of this optimal solution and what advice the bird would give, right? That's what we're going to store for each of these subinstances. We're not going to store the solution. We're going to store the cost of the optimal solution and what advice the bird would give, right? Everybody good with that? Right? So here we're just setting up the table, right? The object, the knapsack could be of size 0 to V. The objects that we need to consider are 0 to N, right? All right, so now we want to set, then we have a little section which says, what are your base cases, right? And I like to not do that first, all right? Because I find it's, what are the base cases? The base cases are those instances that you can't solve by your normal way because they're too small. So I like to, I think if you just bang down your base cases here, you might get them wrong. All right. So
I
I'm
have a
gonna
question.
what? Yeah.
I'm a bit confused about why we like have the word base case in an iterative algorithm. Isn't that a recursive thing?
Good question. Good question. So we need to solve all of these subinstances, right? We have a whole bunch of subinstances here.
Mm-hmm. Yeah.
And the order we're going to solve them is from smallest to largest.
Yeah.
Right? And the reason we solve from smallest to largest is that when we're solving one, we're going to need help from the other ones. We're going to need help from smaller ones, right? And so if we solve the smaller ones first, then when we need help, they will already be solved, right? Does that make sense?
Mm-hmm.
All right, so forget the word base case right now.
Okay.
Right? Let's skip it and go on to the rest. And then we'll remind us that we need to go back and ask about base cases. All right. All right. So what are we doing here? Well, the first big loop is to loop over all the subinstances that we need to solve. All right. And so this is just, I have two loops. Why? Because it was a table of states, right? Table of subinstances. So I'm just looping I equals 1 to N. The volume of my knapsack is 0 to V, or actually probably it should be 1 to V. I think that's a typo, change it to 1, but don't worry about that. I won't take off any marks if that was wrong. Everybody good there? We're just looping over all subinstances. You can see it, we're kind of doing it from smaller to larger, right? All right. So now I'm saying, let's focus on, I'm really obsessed with you not trying to solve everything at all at once because you'll panic and drown, right? So focus on what your job is. All right, so here's comment. I'm focused on solving this particular subinstances, right? Which is how to fill in the table indexed by this. I have to know which of these first I objects put in my knapsack besides V prime, right? All right, so now how do I solve that problem? Right? Come over. Did I turn it around? I guess I didn't turn it around. Right. Well, my job is to put the first I objects into the knapsack, right? And I don't know how to do that. As people have said, it's hard to figure out what to put in the knapsack, right? So I am going to pretend I have a bird. And I'm going to ask the bird a little question about the solution, right? And that's where we have what I call the bird friend algorithm, all right? And so one of my questions I'm going to ask you on the test is to give me the bird friend algorithm. All right. So what will the bird friend algorithm say? It'll say, what is my problem? My problem is this V prime I problem, right? I have to know what my problem is, what my instance is. And then I ask the bird a question. I'm going to ask her, and I want to ask her something about the end of my solution. And you could see why is because what we want our friend to be, right? Right. My instance is the first I objects, and my friend is going to be first I minus one objects, right? So what do I need to learn about myself is the ith object, right? Does that make sense? The difference, if my friend is Mr. I minus one and I'm Mr. I, then my job is to deal with I, right? So I asked the bird, do I put the ith object in the knapsack? Yes or no, right? And she's going to give me one of two answers. She's either going to say exclude the ith knapsack, or she's going to say include it, right? So for each of those answers, I'm going to pretend for a while that she gave it to me and I trust her. All right. Now, the truth is we don't have a bird. So we're going to try also all possible answers. We're going to try her answering exclude and try answering include, right? And I've numbered them with integers here so that you can store them in the table. All right. All right. So she's going to answer something, right? And let's say she answers exclude it, right? If she answers exclude it, then I'm going to delete the ith object. She told me the ith object's not in the solution, right? So now I just need to worry about the ith minus one objects, the first I minus one objects, right? And how big is my knapsack? Well, it's the same volume it was before, right? So my problem has gotten smaller, right? Because the bird helped me, my problem got smaller, right? Now, instead of me having this problem, I have this smaller problem, right? And how am I going to solve this smaller problem? I'm going to get my friend to solve it, right? That's where the friend comes in. I asked my friend, hey, friend, how do I put the first I minus one objects in the knapsack of size volume V prime? And my friend's going to tell me, right? And then what will my solution be? My solution will be the exact same solution he gave, right? Whatever he told me to put in the knapsack is what I'll put in the knapsack, right? Because why is it the same? It's because I'm excluding object I. Why? Because the bird told me to, right? All right, let's look over the other case. Suppose she tells me to put the object in, right? If I trust her, then what do? I put it in. Now, my knapsack, instead of being of this size, is a little bit smaller, right? Smaller by the size of the object. And I don't have to worry about object I anymore, do I? Because we've decided about it. So now this is what's remaining for me to determine, right? Does that make sense? And how am I going to solve it? Is I'm going to ask my friend. And so my friend will tell me, if you have a knapsack of size V prime minus VI, which of your first I minus one objects do you put in it? And the friend tells me the optimal solution, right? And the way I get it from my friend is I look it up in the table. And then what is my answer? Well, in this much of the knapsack, I do exactly what the friend told me to do. And in the last VI of the knapsack, I put object I. Right? Does that make sense? All right. So that's the bird friend algorithm. You understand the bird friend algorithm? When you have a bird who gives you the answer. All right. but we don't actually have a bird. So what we're going to do is we're going to try all bird answers. And sometimes if K has a lot of possibilities, this will be a loop, right? But now it's not a loop because there's only two options and we do very different things on the two options. So it'll be a not a loop, but case 1 and case 2. All right. So what do we do? Not case 1 and case 1 is you exclude. So here, I'm calling it optimal solution sub what? That is my problem, right? So I want the best solution to my problem that's consistent with the bird telling me 1, right? Well, this down here is the optimal solution to my problem. That's the best solution consistent with the bird saying 2, right? K equals 2. So let's see how we compute those. Well, as we said, if she says exclude it, then I ask the friend this sub-instance, right? The knapsack, the I is 1 smaller, but the knapsack's the same size. And my solution's the same as my friend's solution, right? Does that make sense? And, but
Yeah,
here
so for the friend bird method, the friend here is essentially either a table lookup or a combination of a table lookup and some computation.
no,
And the bird here,
friend is the table lookup.
but
looking at
it could also, yeah, it could also be like a computation involving table lookup, not just a simple lookup,
No,
because
well, let's wait till we get down here. I'm going to say no. The friend is the table lookup, but my answer is a combination of the friend answer and the bird answer.
okay, got it.
Right. All right. So here, if the bird says yes, put it in. Then what's my answer? Well, I give my friend a knapsack that's smaller because I put it in, and the friend only has to worry about the first I-1 objects, and my friend gives me the optimal solution, and I then add to my friend's solution the fact we're taking object I, right? And what's the cost of my solution? Well, I take the friend's cost, and I add on the cost of object I, right? Remember, this is the cost of that last edge, right?
Can you explain the union I again for the optimal solution?
Well, here a solution is a set of objects, right? It's a set that we're taking. So the friend is giving me a set of objects from the first I-1 objects that we want to take. And I'm just adding object I to it.
Okay.
Right? I could have put a plus here, that, a set plus an object, but I guess I put a union because I felt it was like a set.
Okay.
Right, and note I commented out the solution part because we're really only doing the cost part. Right. Now there's another nuance that I didn't talk about before, and that we really can only put the object in if the object fits in the knapsack.
Yeah.
Right. So here I'm testing, does the object fit in the knapsack? And if the object doesn't fit in the knapsack, then shoving it in would be really bad.
Right.
Right. So then I would say the cost of this solution where I shoved it in would be negative infinity because I'm trying to get the highest solution possible. And this would be a really bad solution. Right. Does that make sense?
But aren't we like imagining that the bird is like some sort of like an oracle that is like never wrong?
Well, so yeah, I'm happy with that. I mean, here I'm saying if she tells me 1, then this will give me the best solution. If she tells me 2, then this will give me the best solution. Right? So this is the bird friend algorithm when I know she's saying yes. And this is the friend algorithm when I know the bird's saying no. Right? And now we can scroll down a little bit further.
I mean, the else statement, which says like the bird is wrong, so we end up having a cost that is like negative infinity.
Yeah, don't get too scared about this, right? Let go of that worry. This is just one little nuance where if it doesn't fit, then the bird shouldn't be giving us that answer.
Okay.
All right. Really, there are two cases. The case she says yes, the case she says no.
Okay.
Then we come down here. Now, we didn't know whether the bird should say yes or no. So we tried them both. And now for both the yes and the no, we know what the best solution to our problem is consistent with that bird answer, right? And what do? We figure out which of those two answers is the best. Is it the k equals 1 or the k equals 2 that's best? And we just figure out here which one's the best. And we store remember our problem was to store this instance, the cost of this instance. And whichever one's best, we store in there. And in Bird's advice, we store which one is best. And that's the entire algorithm, right? Does that make sense?
Can you also explain like that part, like after the and for, there's an
Now,
optimal solution that says knapsack with advice.
right. So here, I'm saying you don't actually have to worry about this too much.
Okay.
So in the end, we know the cost that, our instance is a knapsack of size V where we have in objects. We have to worry about all in objects, right? This is our instance that we need to solve. And we know the cost of the optimal solution to our instance, but we didn't store it because of these comments here. We didn't actually store the solution, right? So you have to go back and figure out what the actual solution is. And so I'm just saying here, now we have the bird's advice, go back and do it again. But I'm not requiring you to figure out how to do that.
Okay.
Right. All right. So do you understand this part?
Yeah. And then you said we would also go back to the base case part.
Now, that's what I'm going to do now is I'm going to go exactly what I was going to do. Is
Okay.
if you understand this, I was going to talk about the base case.
Okay.
All right. So now I'm saying we need to have, before we can solve a problem, we have to solve our friend's problem, right? So for example, if my I is 5, then I'm going to have my friend will be 4, right? If my I is 4, my friends will be 3, right?
Yeah.
If mine is 1, if my I is 1, then I'm considering the first object. So who will my friend be? My friend will be 0, right?
Right.
Now, do I have a friend who's 0? What does my friend 0 job? My friend 0's job is to consider no objects.
Right.
Now, will this code work when I is 0?
No.
No, because he will ask for a friend who's -1, and we definitely don't know what that means.
Right.
Right? So I'm going to check which of the instances don't get solved, right? Which instances don't have friends, right? So when I is 0, he doesn't really have these friends, does he?
Yeah, no, he doesn't.
Now, let's say the same for our volume. Here we're making our volume smaller, right? So what happens if our volume's already 0?
It would end
Right?
up being negative.
We can't make it smaller, right?
Right.
All right, so then I'm going to say that the sub-instances that we don't know how to solve yet, but we need to be solved, is when the V is 0 or when the I is 0, right? If you look at our table over here, right? Here, I thought I'd turn the table around where if this is me, then my friends here are my friends. In fact, let's find the other. All right, so here, right, instead of saying my friends are forward, my friends are back, right? This here, this guy has this friend and this friend, right? And this guy has this friend. So who don't have friends, right? This 0 guy, he doesn't have, he wants this friend, and this friend, but those aren't really friends, are they? Right? So these are all my base cases, right? These are guys that my other algorithm won't work for, right?
Right.
So over here, we have to solve the base cases. And what are my base cases going to be? Oh, we look like my base cases are when the number of aisles. Oh, we don't want any aisles. Sorry. The base case is when the number of objects is 0, right? Or when the knapsack is of size is empty, right?
Right.
Those are our base cases. And what is our answer? Well, if I is 0, then we know that the solution is kind of the empty solution of volume 0, right? Because we have no objects. So there's nothing you can put in. So the cost will be 0. And here, when the volume is 0, then we right? Then again, the volume 0, so you can't put anything in it, and the answer will be 0. Does that make sense?
Yeah, that makes sense. Thank you so much.
Those are our basics, right? They're the guys that are so small that they don't have friends, right? And
Right.
you could see it was easier to solve this first, so we know who our friends are. So then you can come over and think, oh, who our base cases need to be.
Right. Can you go to slide 245?
240. I'm on 245.
This one, yeah. So in this one, which instance friends and the birds, and which instance is ours?
Right. My instance is v prime I.
Okay.
The bird doesn't have an instance. The bird, I asked the bird about a solution. The bird has a solution to my problem, and I asked, do you put the ith object in or not? Then I have friends for each bird answer. I have a question I ask my friend.
Okay, so in this equation, the thing on the left-hand side is like our instance, and the thing on the right-hand side is the friend.
Yes, this is us. This is the friend. Exactly.
Okay.
And the case is the bird answer. Right. We do this if she says yes, and we do this down here if she says no. No, this was yes and this was no. Right? Does that make sense? Right?
Right. Okay. Oh yeah, I have one more question. If we go to slide 34. Yeah. Here I got a bit confused because it says like you cannot ask a second question from the bird, but then on like slide 37, we actually ended up asking a second question from the bird. So the first question was that we asked at node T in this slide. And then it said that we cannot ask her the second question, so we gotta ask a friend. But then when we went to like slide 37, at V7 node, we asked the bird a second question. So I got confused. Like, you know, the dark blue arrow that says that that's the bird, and then the light blue arrows are the friends. So I got confused. Why did we ended up asking a second question from the bird?
All right. So maybe the first and second is confusing here. I was saying, if I want the best path from S to T, then the first question I might ask the bird is what's the last edge? And then if I kept going, I could move up there and then ask her the second last edge, right?
Mm.
But I'm saying we don't do that. We don't have her tell us about the second last edge. Instead, we ask the friend what the shortest path is to get here, right? That's what I meant by that. And here, it's each of these guys is a different Pooh Bear, right? A different subinstance. So this Pooh Bear right here, he needs the best path from S to this node, right? What is he trying to learn? That's the answer that he's trying to learn, right? And how does he compute it? Well, he asks the bird one question, which is, what's my last edge? And she might give this answer, right? Or she might give this answer, or she might give this answer, right?
Oh, so the one that asked the question at node T, that was a different subinstance, and then the one that's asking the question at V7 is a different subinstance.
Yes. The Pooh Bear sitting here is Mr. V7. Pooh Bear down here is Mr. T.
Okay. And then you would have another Pooh Bear that would be at V6 and another Pooh Bear that would be at another.
Yeah. So here I'm saying loop invariant is, suppose that here do I have a loop invariant? Here's my loop invariant. I say, suppose, but we've all these Pooh Bears. See all those Pooh Bears up there?
Right.
All done their job and they filled in this table here, right?
Right.
Then Mr. Pooh Bear 7 is going to ask his bird, which of these edges do I follow, right?
Right.
And he's going to take the best of the best. And then he will be done, right? He's done now. He's done. And so then we move over to Mr. Pooh Bear 8. And Pooh Bear 8 will ask his bird,
Right.
what's his last edge, right? And then we go over to Pooh Bear T, right? And Pooh Bear T has 4 possible answers, right? Does that make sense?
Right. Yeah, that makes sense.
So remember the code, the outer loop was loop over all subinstances, and I told you only to worry about one of them, right? So if we're here, then we've looped over all of this, and now you're worrying about this guy, right? And then the code says, if this is you ask the bird a question, what's my last edge? And you loop over all the possible answers K that she might give you, right?
Right.
Those are the 2 loops.
Okay, and then one more question. So the knapsack example we did, that was like the game of life.
For everyone, we're thinking about it as a game of life, and then we're thinking about it as a bird friend algorithm, and then you're filling in the code.
Okay, so when we were moving like from state to state, that was game of life, and then when we were doing the algorithm, that was bird friend algorithm.
Yeah, exactly. Let me what am I doing here? I'm going here to here. What am I doing here? Oh, I'm going down here to our steps. Steps, dynamic programming. So here, last class I banged in here various the questions that I'm going to ask. In fact, I copied this directly out of your test, right? So I'm going to give you some problem, and you're going to have to think about the game of life. What does Pooh Bear remember so he can continue? How do you index the states that he might be in? What actions does he take from wherever he is? What actions does he take? The bird tells him which one to take. Describe the nodes that are in your graph. Describe which is S. Describe which is T. Describe what the edges of your graph are. Describe the weights of the edges, right? Give special thought to the edges into T, right? Does that make sense?
Yeah.
Make sure your graph has a one-to-one mapping between the solutions of the problem and the paths in the graph, right? So you see how we did those things, right? So let's go through and answer them for the knapsack, right? You'll say, I'm going through the game of life. I'm considering the objects in the objects that I need to consider one at a time, and I decide which one to put in the knapsack. What do I remember about my past? I remember which object I'm considering next and how much of my knapsack I filled so far. I'm going to index those by I and J or I and V prime, right? So now suppose I'm in a particular state. I have a particular I and a particular V prime. What actions could I take? I could put I'm considering the I object. I ask the bird, do I put it in? Do I not put it in? Right?
Right.
And then then what will my graph be? Well, what will my nodes be? My nodes will be for every I and for every V prime. I will have a node which corresponds to the subinstance of the ith object in the knapsack of volume V prime, right? What will be the source node? So source node S will be my knapsack is empty and I haven't considered any objects yet. I'm ready for the first object, right? The sync was a little tricky. Oh, well, let's do edges first.
Okay.
What are the edges? Well, from any node, I V prime, I have an edge that says, yes, put it in, and an edge that says, yes, don't put it in. No, don't put it in, right?
Oh, wasn't the edge the price?
Well, the edge, we have one edge that says, put it in, and then the weight of that edge is the price.
Oh, right.
And if the edge is no, don't put it in, then the weight is 0. Right? Does that make sense?
Yeah.
So
then the sync node T would be, we have put all of the objects that are within the volume.
Yeah, but remember I have to give special thought to edges into T. Why is that? Because I could say node T is the knapsack's full and I've considered all the objects, right? Yeah, but the knapsack might not be full. So I put in these extra edges from not full knapsacks to full knapsack, right? Remember that?
Yeah.
That's why I gave some extra thought to that. And we made sure that we had fewest edges possible because our edges are short, right? They're atomic edges. If they go from I to I plus 1, then we only have 1 or 2 edges per node. If we go from I all the way over to I prime, right, then we might have n squared edges, right? Does that make sense?
Yeah. So for the sync node T, in the describe part, yeah, the sync node T would be we considered objects that almost fills the knapsack, but doesn't necessarily have to fill the knapsack.
Yeah, and then there's one edge to T. Yeah, exactly.
Okay.
Yeah. The order, I have it in this order, but when I wrote up my answer, I describe the nodes, I describe S, and then I describe generic edges, so we kind of understand the graph. And then at the end, I talked about having a single T and what edges will come into it.
Mhm.
Sorry, I have a question, Professor.
Yeah.
So the weight of the graph means that with the weight source, the edge weight from the source node S and to the T, right? In the
Yeah.
best case.
Yeah,
best
sorry, can you say
case.
your question again?
Yeah. I mean, you said that if we do not choose the edge, so the weight of the edge will be 0, right? You just said that.
Yeah.
So the weight of the resulting graph means that if we choose the best solution or for the every node, and this will result a path from S to T, right? And the weight for every edge in this path, it is the weight of the resulting graph, right?
Yeah, some of the things you said made me nervous. When you said we take the best edge for every node,
Yeah.
well, I don't know how to take, again, we don't know how to take which edge. We don't know whether to take the bird or not the bird. Or we don't know whether to take the ith object or not. So we don't know which of these two edges to go. That's not my problem.
Yeah.
But here I'm saying, right, be sure there's a one-to-one mapping between solutions to this problem and paths, right? How do I'm not asking you to actually, to discuss this, just to think about it, to make sure you're doing it right. So what's a solution? A solution says what to put in the knapsack and what not to put in the knapsack, right?
Yeah.
So if I told you a solution, could you find me a path? Sure. Right? You start at node S, which has which first considers node 1, and you either follow, if node 1 is in the object, is in the knapsack solution, you follow take it. And if it's not in the knapsack solution, you follow don't take it. Right? So you keep following for each object, you follow take it, not take it, based on what your solution says. And in the end, you get a path, right?
Yeah.
Every solution gives you a path. Similarly, every path gives you a solution.
Yeah.
And their costs are the same.
So I mean, and then we get the path from S to T, right?
Yeah.
And the each and sorry, sorry, I made mistake. Sorry, it is the edge weight. I thought that is the weight of the whole graph.
Yeah, no, it's just the edge of the wedge. At each edge has a weight.
Okay.
Right?
Sorry. Yeah.
If it's no edge, it has weight 0. If it has a yes edge, the weight is the price of that node.
Yeah.
Right? Does that make sense?
Yeah, thank you.
Price of that object. So then that's this question.
Mhm.
Then down here, we want to start warming up to writing actual code and making it more aesthetic.
Mhm.
So the way I would start by thinking is, what's an aesthetic set of subinstances? And the aesthetic one would be, I'm going to have an I and a V prime, and the I is going to tell me which objects do I need to put in the knapsack, and the V prime will tell me the volume of the knapsack so far, right? So that's what, right? The input tells me the volume V prime of the knapsack, and it tells me I have the first I objects, and the output tells me which of those I objects do I put in the knapsack. What do I ask the bird? Do I put the last object in or not? What does she do? The answer she gives me. She gives me yes or no. If she says no, then what subinstance do I give my friend? Well, I give him the exact same volume, but one less I minus 1 objects.
Mhm.
What does he give me? he gives me which of those I minus 1 objects to put in the knapsack. What's my answer? My best answer of filling the knapsack with the first I objects, consistent with the answer, don't take the last object, is going to be the same as my friend's answer, right? If on the other hand, she says yes, then what do I give my friend? I give the same, I give the volume minus the volume of object V and only I minus 1 objects. And then what is my answer? It's the same answer as my friend plus object I, right? Does that make sense?
Yeah.
And then maybe I think I might have even moved this later already. Let's move that later, right? I'm going to tell you to complete these lines of code. So in this one, you loop over all subinstances. So you loop from I equals 1 to N, V prime equals 1 to V. You loop over all of those, right? Then you loop over all the bird answers. Well, she's either going to say yes or no. So then there was the answer when she says yes, the answer when she says no. Right? Does that make sense?
Yeah.
What are our base cases? Well, when I is 0, our base cases. When V prime is 0, our base cases. Right? What's our running time? Well, the number of subinstances is N times V. The number of bird answers is 2. Right? So I multiply those to get big O of N times V. Right? Does that make sense?
And we also do like 2 to the power of number of V's, right?
Well, if it so happens that V is not really, is stored in bits, then you might have to do that. But let me just tell you, that's not going to be an issue in your test.
Okay. All right. Thank you so much. This helps a lot.
Is it good? You think you can do it?
Pardon?
You think you can do it?
Yeah.
Excellent. All right. Well, then it's 4 o'clock. So we'll stop and we will talk again. I guess we'll be back in class on Monday. Everybody good?
Yeah.
All right.
Thank you so much.
Bye, everybody.
Not.
Thank you, Jeff. Bye.
Have a good weekend.
Bye,
Bye.
Professor.
Have a good weekend.